you need to tell me the answers. Okay. So we will see some problems. You need to tell me the answers for these problems, right? So these are all simple based on the concepts that we saw in previous cases and all. So I'll just tell you the problems. You will tell me the answers, because just to make our minds clear and to refresh before we are going to the next topic. So chats, everyone ready? So first thing, we will start with something simple. So what is the probability that you will get a 9 of spade? What's the probability that you will get a 9 of spades out of a deck of 52 cards? Answers? Answers out of 52 cards. I am choosing a 9 of spades. What's the probability that I will get that? Answers? Chat. Okay, so I have total 4 suits, each suit 13 cards. Right. So 9 out of spades is just a one single card out of my total set of 52 cards. So the probability, I have only one favorable case out of the total 52 number of cases. So in this case, my probability will be 1 by 52. So now we will go to like add on to this like some more cases, and then we will try to solve that. Then now I will tell, instead of 9 of spades, I will tell what is my probability of getting a 9. What is my probability of getting a 9? Again, if I draw a single card from a deck of 52 cards. So again, as we know, what answers you can give in chat. So as we saw, the denominator will be same. I have total 52 options. So what will be the numerator in my case, in this case? In how many ways can I get a 9 out of the deck of 52 cards? Answers? Yeah. So I have, as we told, 4 suits in this. Each suit is having a 9. So I have 4 possibilities in which I can get a 9. Right. So my probability of getting a 9 from a suit of 52 cards is 4 by 52. Similarly, the other case, spade. What is my probability of getting a spade out of a deck of 52 cards? So what's the probability in this case? So as we told, in a deck there are 13 cards. So the probability of getting a spade is 13 out of 52. Okay, so that much we covered in previous session anyway. So we will just build upon from that point. So then my first question is, what is the probability that a card is a face card? So as we saw, a face card is a king, queen or jack. And I have a king, queen and jack corresponding to all 4 suits, right? So I have like 3 into 4 equal to 12 number of favorable outcomes. Again, total number of outcomes is 52, right? So next thing you can solve. You can tell me the answer. What is the probability that it is neither a diamond nor a face card? So one thing you can do is we can find the probability that it is a diamond card as maybe A, and find the probability that it is a face card as B. Then you can do the intersection of both these, and that probability you can subtract from 1. This is one way of doing this. There are like many ways of solving each problem. So we will proceed to this route. So now what is the probability that I will get a diamond? That I already saw, right? Probability that I will get a diamond is 13 out of 52. And the probability that I will get a face card I solve here 12 out of 52. Right. Now here we cannot add these two. Like when we went through the addition rule, we saw that here A and B are not independent events. So if they are independent events, then probability of A, sorry, it's my mistake, it's a union here. Probability, we saw that in addition rule, probability of A union B is equal to probability of A plus probability of B if both these events are independent. But in this case, there's a probability that it can be a diamond as well as a face. So these events are not independent. So I have to like subtract the cases where both these are there. So if you see how many face cards are there in diamond. So from here we can see that there's a king, queen and jack in diamond. So 3 out of 52 I have is my third factor here. So I got my one factor as 12 by 52, second factor as 13 by 52, and third factor as 3 by 52. So finally the union I will get as 12 plus 13 minus 3. So that is 22, right? 22 out of 52. So my question is, which is neither a diamond or a face card. So I have to subtract this from fund. So finally I will get the answer as 1 minus 22 by 52. That is 30 by 52. Now similar way same question. You can write this as on your own later. I'll just tell the answer. You can write on your own. Same way that we did now. What's the probability that it is neither a 10 nor a king? You can solve it the same way that we did. Finally, you will get answer as 44 by 52. So you can just write out same way that we did the neither is a diamond nor a face card problem. So we'll move to the next problem. Like now we draw a single card and we saw the probabilities of this. Now we will try to see multiple cases like similar to combinations that we saw in previous case. So here we will see what is the probability 4 cards that instead of 1 card that we saw in earlier case, I will choose 4 cards from a suit of 52 cards. Right. So my statistics or n points remain the same. So now I will try to see the probability that what's the probability that all 4 cards are the frame from the same suit. So I know that in a single suit 13 cards are there. So the number of ways in which I can choose 4 cards out of that is 13C4 and my net number of cards is 52. So from that I have to choose 4 cards. So 52C4 is my denominator. Now tell me, is this the correct one? Will this do, or am I missing something here? I am telling that I have to find the probability that all 4 cards are from the same suit. And I'm telling that in a suit there are 13 cards. So the probability, the number of ways in which I can choose 4 cards out of that is 13C4. Yeah, right. So now here we have not considered the fact that we have 4 suits. So like corresponding to each suit, I have 13C4 ways of choosing 4 cards. So my net probability will be 4 into 13C4 by 52C4. So we will not try to solve this handout because numerically you can solve it using a calculator or you can directly find it out. We will just tell you how you can. We will just see how we can solve these type of problems. Now next thing, similar question we will see, but here we will put a restriction that 4 cards are there, but I need to find out the probability that each of the card is from a different suit. So that means I take 1 card from one suit. The next card will be from some other suit. Again 13C1. Similarly, the third card is from a third suit. And the fourth card is from a fourth suit. So my denominator is again same. 52 cards. I need to choose 4 cards. So this way, like depending on the problem, we will have to make use of find out how you apply the combination equations that we saw in the previous examples. Now this is like same thing that we saw in previous class. I'm just repeating since this will be like useful when we go to our subsequent discussions on that distributions. So now let's move to a somewhat more difficult question. This is not difficult, but you will have to think it out, like why it is coming like this, right? So here, similar to our conditional probability, like we saw conditional probability. I hope you guys are remembering. We saw that probability of A intersection B is equal to probability of A given B into probability of B, or probability of B given A into probability of A. So we saw equations in previous class. If you have any doubt, you can go through that. So this probability of B given A and probability of A given B are called conditional probability. So the probability of two events, intersection of two events can be found out using like these equations. So we will try to solve these two problems using this conditional probability equation that we saw in previous class. So it is like problem statement is like this. The car will be ready for shipment on time with a probability 0.85. and that is what, let me suppose it is an event A or B, that is 1 out of that, and it is ready for shipment on time, and delivered on time is 0.75. So find the probability that it will be delivered on time given that it was ready for shipment on time. So here we are supposed to find out this intersection probability, that is it was ready on time and it was delivered on time. So from this we are told that it is like made ready with a probability of this thing. So we are supposed to find out the probability of A given B here. So what we have to do, we have like change this problem to what way we want. So I am supposed to find out the probability that the car got delivered on time, provided it was made ready on time, which is the probability that it is, that is my intersection case, ready as well as delivered on time, divided by the probability that it was ready on time, which is 0.85. So this way, like probability of A given B, you found out from the conditional probability equation that it is probability of A intersection B by probability of B. The probability of A intersection B is given here as 0.75. It is ready for shipment on time and delivered on time. So and thing you, if you see, that will be my intersection case. The probability that it was ready for shipment on time was 0.85. So 0.75 by 0.85 is the probability that I am required to find out here that the item car will be delivered on time, given that. So whenever there is a statement like given that, you have to think that it is, you are asked to find some conditional probability. Then we will go to a similar example. 0.65 is the probability that there will not be any strike, and in case there is a strike, there is no strike, the job will be completed with a probability 0.2, and in case there is a strike, it will be completed with a probability 0.32. So now here you are supposed to find out the probability that it will be completed on time. So this is like similar to, there is a probability that I am asked to find out the probability of something like A union B, whereas A is the probability that there is a strike and the job got completed, and probability of B is that there was no strike and the job got completed. So in this case, my probabilities are probability of A and probability of B. So and both these cannot occur together, right? So there can be a strike or there cannot be a strike. So I need not consider the intersection case here, since both these are independent events. The probability of A is my probability that there is a strike and it was completed. So that case, so from this I can know that 0.65 is the probability that there is a strike, and 0.35 is the probability that there is no strike. So in case there is no strike, I can complete it easily. So that is why the probability is more here. So 0.8. So the second case is there was a strike, and in this case the probability that I will complete the job will be less. So this will be my, similar to our previous case, another example of conditional probability where we are given values like in case there is a strike and in case there is no strike. I am given the values and I am asked to find out the probability that I will complete the job on time. So now we will go to a somewhat interesting problem. So this thing, like this is also what we saw in previous class, Bayes theorem. So but we will try to solve it without using Bayes theorem. We will try to solve it like intuitively. So like similar to what our tree kind of thing that we draw earlier, we will try to solve this. So I will write the problem statement in similar to a diagram. So here, as you can see, everything is talked about 60%, 10%, 80% and all. So since percent is with reference to 100, so I will assume that suppose there are 100 students in a class, employees in a company. So I will write the problem statement based on this. So it is told that out of this 60%, that is 60 people are college graduates. So that means the remaining, that is 40 are not college graduates, right? So out of the college graduates, it is told like 10% are in sales. So 10% of 60 will be like what? 6. So 6 people are in sales and the remaining 54 people are not in sales. Okay, now coming to the next statement, of the employees who did not graduate from college, which is 40, 80% are in sales. So that is 40 into 80% of 40, that is 32. So the remaining 8 people are, 32 people are in sales and 8 people are not in sales. A person is selected at random and I am asked to find the probability that the person is in sales department. So I know that 6 people here and 32 people here are from sales department. So from the diagram itself, I can infer that the probability that if I choose a person at random and that he is in sales department is 6 plus 32 out of the total number of people that I have 100. 38 by 100 will be the probability that the person is in sales department. Similarly, the probability that the person is neither in sales department nor is a college graduate. So I have to see the people who are college graduate, that is not college graduate, that is 40. Out of that, people who are not in sales department, that is 8. So the people who are neither college graduate nor in sales department are 8 out of my total 100 employees. So that probability will be 8 by 100. So now in a simple problem like this, we could like easily solve it without using any Bayes theorem or any mathematical foundation, directly based on like intuition. I can solve problem like this. But when you go to more complex problems, we can make use of the Bayes theorem. So same problem we can try to interpret in terms of the Bayes theorem that we saw. So this diagram you might first diagram you might remember from previous class. So we will have like a 1 here, which will be my total probability, and then in one side I will have my one condition that in this case suppose it is like college graduates. I will have the probability that bar stands for complement. Probability that people are not college graduates and the probability that people are college graduates both should add to 1 because everyone will be either a college graduate or not. And then my second case will be my second condition. Maybe the probability that people are in sales department, probability that people are not in sales department, that also should add to 1. Then here I will have the inside. These are called these two, and these two are together called the marginal probabilities. Since these occur on the like margin of my diagram, and whatever is inside is called the joint probabilities. So that this will be the probability that the person is not a college graduate and he is in sales department. The probability that he is neither in sales department nor a college graduate, and this one is he is not in sales department but a college graduate. So that kind of way. Once you define the A and TA events, you can define fill your table accordingly. So same case that we similar to our diagram. If we try to implement it in the previous one that we saw figures, we'll try to populate in this. We will get 100 here. 60% of people are college graduates. That 60 will come here. The 100 minus 60 will come here. So out of this, I am told that 10% are sales department. So I got 6 here. So here this plus this should add to 60. So that way I will get 54 here. And this case I am told that 80% of my people are in sales department. So I will get 32 here. So subtracting 32 from 80, I can fill this. So as you can see here, I am given just 2-3 values out of this. I am given 160 here. I am given 1% here. I am given 1% here. So 3% values I have given. So with that, I can fill this entire table. So and this much once I fill, I can go in the row wise direction to fill 54 plus 8 as 62, 6 plus 32 as 38. And as a confirmatory check, you can see that 62 plus 38 also should add to 100 because both ways it should come. So this can be used as a confirmatory check that whatever calculation you did are correct. Now once you make a table like this, whatever be the question, you can find all the answers directly from this table. The probability that person is from sales department, the probability that person is a graduate and from sales department, not a graduate but a sales department. All kind of ways think that you can directly pick the value from this, divide by the condition to find out the. So this is one application of a like Bayes theorem. And we will see one more example that we saw in previous class. So you can go through previous class example that we saw. The same example, I have just returned the steps and all so that you can know like I have just filled values and all. So suppose this example that we considered as suppose some percent of people are COVID positive. That is one case. So the rest of the people are COVID negative. Then and I am testing all the people in my population for COVID. Out of that I got a few people as COVID positive, rest are COVID negative. But here there can be conditions like one person who tested COVID positive tested negative when he was like antigen test was done. And some persons who are actually COVID negative got tested positive in the antigen test. So things like that I can solve using this Bayes theorem. So I have given an example here. You can go through this. So similar kind of things when you get problems. A similar kind of thing you can see is a patient goes to see a doctor. The doctor performs a test with 99% reliability. That is 99% of people who are sick test positive and 99% of healthy people test negative. So when you get things like this, what should directly come to your mind is that this is an application of like Bayes theorem. So I given 2 links here. You can go through that. So that is like similar examples, more detailed way how to solve. So once you solve 2-3 examples, you will get a hang of things. So this is like a very simple application with which we can solve like many number of problems. We can like simple ball problem, die problem and all we can directly solve with our minds. But if you get more complex problems, you can make use of this conditional probability Bayes theorem and all to solve your problems. Now we will again go to our simple problems and try to solve them with our Bayes rule. Now these problems may look complex, but these are actually like simple implementations. So we will go with but the things like this you can find in many competitive exams or interviews that you go there. You will mostly find problems like this only. You will not see simple examples like previous ones that we saw, like finding the head 9 out of spade or things like that are actually simple problems. So problems like this only you will mostly encounter when you go for any interviews or things like that. So you'll just see like even if you don't get it in the first try, you don't worry. You can always go through this video later and find out. Of course, when I try to solve it for the first time, you may think that these are difficult. So but okay. So basically the question is like this. There are 2 bags A and B. And it contains white and red balls. So the number of white balls and red balls are given here. In bag A there are 2 white balls and 3 red balls, and in bag B there are 4 white balls and 5 5 red balls. Now I am asked to told me that a ball is drawn at random from one bag and found to be red. So I am told that my probability the ball finally which I took is red. And I am asked to find the probability that it was from the bag B. So as we saw in the previous case, we are supposed to find the probability of what R intersection B by P of B in this case. Right. So basically, I have to find this is an application of our Bayes theorem or conditional probability that we saw earlier. I am asked to find the conditional probability of red ball given that my bag is taken from the second bag B. Now there are multiple ways in which I can solve this problem. So since I have 2 bags, the probability that I can choose any one bag is 1 by 2, right? So probability that I take either bag 1 or bag 2 is 1 by 2. Then the probability that I will take what? Suppose I took the bag B. So out high in that I have 9 balls. So probability that I take a ball from that is 5 by 9, right? So that way, if I choose the second ball, then the probability that I took the red ball is 5 by 9. So my probability that in this case will be half into 5 by 9. So now here, if you recall our discussion on Bayes theorem, this is not the we may be required to find many number of conditions like this, like probability, what's the total probability of taking a red ball, what's the total probability of taking a white ball, what is the probability that the ball was from A or B. That is simple, right? 1 by 2 probability. So you can try to solve this similar questions using Bayes theorem, and we can find the answers. Like I'll just tell an example now. You can think out how it will come. So now my problem was probability of red given black, right? So that I found out as it was 5/9, right? In the black B there are 5 balls. Out of this 5 are red. So total 9 balls. So 5/9 was the probability that it was red given black. Now suppose I am asked the other way around. Suppose the ball was taken from the second bag. What is the probability that it was red? So in this case, if you go same way, then I want probability of again B underscore R divided by probability of R. In this case, actually finding the probability of R is difficult, right? So probability of B intersection R is easy, but probability of finding R in this similar way is difficult in this case, since I don't know, because I can take from ball A, or I can just 8 by total number of balls. So I don't know whether this thing is correct or not. So in that case, I can use the total theorem of probability that we saw in previous class. So that way, what it tells, there's a probability that I may take any ball. So similar to that, I can write my equations using the theorem of total probability and then add up to find the denominator, that is probability of B or probability of R. So you can just try to implement that. I will not go into detail because we already saw this. These are just applications. So given this simple question, we got it as 5/9. So you try to solve it for the other way around. What's the probability given R given B we solved? You try to solve it the other way around. Probability of it was from bag B given ball I choose was red. Now we will solve a better problem here. So once we go through that, the first problem also you will get same way you can try to solve that. So the problem statement is here, but I have 3 bags, and the 3 bags, the number of balls are blue, red, and green. The total number of balls are given. Again, the probability that I will choose any ball is same. Any bag is 1/3. The probability that I will choose bag A or bag, since I can equally choose any bag, right? Now the probability here I am asked to find the probability that the selected balls are from bag C. So let's find out the net probability that, suppose my event here is what, 1 blue and 1 red. So that is my event D here. So let me try to find out the probability that I will choose 1 blue and 1 red ball from bag A, 1 blue, 1 red from bag B, 1 blue, 1 red from bag C, and I will try to add it up. So that will give me the net probability that I will choose 1 blue and 1 red. So from the bag A, I can choose with a probability 1/3. Out of the 1/3, I have 1 blue and 1 red, right? So I need to use combinations here. So out of the 2 red balls, I have to choose 1, and out of the 1 blue ball, I have to choose 1, and total number of balls is 6 by 2. Okay, similarly going to the second bag, 1/3 into probability of choosing 1 blue ball is 2. Out of 2, I have to choose 1. Out of 3 red, I have to choose 1. Our total is 2 plus 3 plus 1, 6. Again 62. The third one again 1/3 into, in this case 3C. 3C1 into 1C1 divided by 62. So this will be the net probability that I will take 1 blue and 1 red ball. As if you see here, you can see that this is similar to our expectation case that we saw. So finally, all these link to same thing, like you can solve a problem in multiple number of ways. So now I found out the total probability of choosing 1 blue and 1 red ball from the all 3 bags. Now the question is find the probability that the selected bags are from ball bag C. So I just have to, this will be my numerator, and in the numerator I will have to put probability of E given that the ball was from the given thing. that will be again 1/3 into my this case bag C, right? So my third case 3C1 into 1C1 by 6C2. So this will give me the answer that the selected balls are from bag C. So same way you can try to answer the previous question also. So this kind things like this may seem tricky, but these are all direct implementations of the conditional theorem, Bayes rule and all. And these are the kind of things that will most probably you can encounter during competitive exams, interviews and all if you attend. So once you solve like 2-3 examples like this, you would be like able to solve any problem. But the one problem that we saw here is here the bags are 2 bags or 3 bags and the type of balls are 2 and 3. We were able to solve easily using direct application. But suppose you have like 100 bags and 10 colors of balls and all things like that, the problem grows complex. So that way we need some other mathematical way to handle problems in that case. For that, what we go for is what is called a probability distribution.